is like 20 to 40 degrees Kelvin. There's no sun. It's really, really cold. And so plastics don't work in that stuff. And the environment you design for as a space engineer stretches the imagination sometimes. And you have to really, really work on what do I have to do here? Because this environment is different.
So, welcome to Sunfiber. This is Alan, and with me today is Dr. Peter Swan, who has been working on space elevators. Could you tell us a little bit about yourself, Peter?
Okay, my background is I've got 56 years of working in space stuff.
Oh, wow.
Basically an engineer, and I picked up a PhD in space system engineering. So that's more engineering in space stuff. And so I really did have a lot of expertise. I've tracked satellites, I've calculated collision, stuff like that. I've built satellites. My first 20 was in the Air Force Base business, and then I went to Motorola and we developed a 92 satellites launched into space for a constellation of communications to handsets, a la Starlink, except 30 years earlier. So anyway, so we had a lot of experience over my years doing all that stuff. Then I've taught, and I still am teaching, and I've advised, and I'm working on the space elevator. I started about 2002, something like that.
Oh,
Then we created an organization called the International Space Elevator Consortium. I ended up being the president of it. And then I've retired from that. Now I'm just chief architect and laying back and doing things. I've got a lot of international connections in that I present internationally at least twice a year. And so it's fun to have such a big challenge. And that's the way I look at it. It will happen. Space elevators will happen. The question
okay.
is, are we going to start them in the near term or are we going to wait? It's a big question, and we're all working that.
Okay. So, why space elevators instead of rockets?
Okay, the space elevators have some very big advantages. And let's talk just logistics. We can get to people later, but if you put people on it, you have to have double cables and redundancy and all kinds of safety stuff. And then there's a radiation to protect them from. So we're planning on letting rockets do the raising of people. And we believe
Oh,
we should have a good team arrangement. We call it the dual space access. And you can see on my background, a student of mine painted this, and she made it so that it's rockets and space elevators helping humanity move off planet. So our task is massive movement of stuff off planet, going to all kinds of locations. And what I mean by massive is like 170,000 tons per year. We'll get to all the details later, but we only put up 26,000 tons between the first space system and only 23 or so.
oh,
20,000 tons roughly. They always talk kilograms. If you talk about payloads, they say kilograms. They don't know what the word tons means, really. So, what we
right.
do is we're proposing to do massive logistic support to humanity's move off planet. We also support planetary stuff like communication satellites and space solar power and stuff like that. But the real kicker is we move off planet. Now, what's a big deal about that? And the answer is we provide 70% of the mass at the pad to the destination, be it the orbit around Moon or Mars, whatever, but we provide 70%. Now, the rocket equation is a silly thing. It works, and we have had a very, very good history of using rockets, and I love rockets. I've been in a lot of rocket launches. But we put 1/2 of 1% of the mass that was at the pad on Apollo 11 to the surface of the moon. 1/2 of 1%.
Oh, wow.
The rocket equation says you can put about 4% to low Earth orbit. And then we can put 2% to geosynchronous, 1% of the mass on the pad around the moon and Mars, and less if you have to land because you got to slow it down and put it on the surface. So we're really talking about a catastrophic equation. Now, Mr. Musk and others, Mr. Bezos and some Chinese, are doing very, very good jobs in reusability. And that's an excellent idea at the lower cost. But
Mhm.
it does not increase the efficiency of liftoff. The rocket equation burns fuel and it throws away metal. And the SLS current plan is to do exactly that. The same thing we did with Apollo, which is throw everything away except for the capsule with people on it, land that in the ocean. So the equation called the rocket equation is catastrophic. The raising of payloads with electricity has many, many factors that are beneficial. One is you get 70% up there, but also it's environmentally friendly. So we call this a green road to space. We don't burn any materials in the atmosphere, and we don't leave any debris along the way because we put it all in a capsule, and then we raise that capsule with electric motors, and it goes all the way to the tip at the apex anchor. And then it releases to places like Mars. We had some students at the Arizona State University do about 3 or 4 years of study. They came up with a report or two and some papers published that said we can put 70% of the mass from the pad in orbit around Mars. We can leave every day of the year. And some of the trips are 61 days long. Some are 400, but the average is around 140. But the kicker is we don't wait 26 months between launch opportunities, which occurs when you use a rocket equation and have to do minimum energy transfer to Mars. Then the planets only align once in a while, like every 26 months. So we wait 26 months before we go to Mars every time. What we're saying in space elevators, you climb to the top of the space elevator and release any day you want. The duration of the flight is variable, of course, because the planets keep changing. But there are times when once every 26 months, when it gets close, we can do it in 61 days. So the revolution that can occur by providing high energy to payloads, raise them above the gravity well, and rotate with the Earth gives you rotational energy. You get tremendous energy, you release, and you go almost anywhere you want, any place in the solar system.
Okay, so tell me about the material that you'd be using to make
the puzzle.
Is it Islands in the Sky by Arthur C. Clarke, where he described building a bridge using diamonds?
Correct. That's what we're going to do. Oh, his concept was based on a lot of fiction. The concepts we're talking about today have been produced. I didn't bring it to my table here. I have a little piece about this big of what's called graphene superlaminate, which is a two-dimensional material. Now, that's kind of hard to comprehend. It took me a while to figure this out. But if you have one atom thick and you have a width and a length, it's a two-dimensional material. There is no third dimension. So it's called two-dimensional. It's a newly discovered capability, and there was a Nobel Prize awarded about 12, 13 years ago, the University of Manchester and one other. They discovered that some materials grow in two-dimensional structure. So what we have to do is figure out how to do that. What we put is we take a CH4 chemical and we put it on a really, really hot surface, and the hydrogen boils off and the carbon sits there. And so they did bonds in a crystalline-like shape, like diamonds, actually like diamonds. It's atomic bond, 1-to-1 atoms, and it's width and length and no height. So we have two-dimensional materials. There are about 10 materials that have been discovered that are two-dimensional: hexagon, boron, nitride, and graphene are the two I know about. And they've been grown, the graphene one has been grown in South Korea to 1,000 meters, a quarter meter wide and 1,000 meters. Now, this is what's called polycrystalline graphene, which is not exactly perfect, but it's pretty close. To be perfect, it would then be called graphene superlaminate. That would have no flaws in the bonding. However, the polycrystalline graphene has been built into long segments, 1,000 meters, and they've been tested at somewhere around 60 or 70 gigapascals. Now, don't ask me what a gigapascal is, I don't know, but it's a measure of strength in tension. And we have materials today that can get up to 2 and 3 gigapascals. That's it. The best materials in the world are single-digit gigapascal tensile strength. We're looking at 60 to 90 gigapascals for polycrystalline, which is not exactly perfect. And we're looking at 120 to 150 gigapascals for the graphene superlemon. So we really have the material out of the lab. Well, it's in and out of the lab. They're still doing heavy research on
Oh
that.
yeah.
And they've taken the production of polycrystalline and extended it to 1,000 meters. The single crystal graphene is all still in small segments, small little sheets. And I have 2 or 3 of those sheets that are layered. So I have a 5-layer copy, a 10-layer copy, and a 20-layer copy of single crystal graphene. So the material has been produced the way we would want it to be produced, except in length. And that's just a matter of forming it and having it come out of a process. I just say I'm not a manufacturer, so I know how hard it is. It's really hard. But the point is that it's there, and we've got like 6 to 8 years to work on that stuff. We don't need it tomorrow. We've got a lot of other things to do. But I claim we now have the material for space elevator tethers. And it's not just one, it's like 3 or 4. I know boron nitride has similar characteristics, so that's 2. And I'm not an expert, but I would wager that a few of those others also have the same characteristics. They're atom to atom bonding, so they're atomic strength instead of chemical strength, which would be molecule to molecule. And so that's the jump in technology that enables space elevators. We can do all the rest of it. They're difficult. Some difficulties we got to worry about, getting power to the climber and things like that. But it's all doable. We've done stuff like that in space before. So the real kicker was the material. And now we have the material halfway out of the lab. Polycrystallines out of the lab. The others not quite there. But there are a lot of people working on it. And so it's a very interesting time of life and development of new stuff.
So this is like really, really thin.
Yeah, one
Like
atom thick.
one atom thick, and even when you have like 20 layers, it's
Right.
still it'd be almost transparent, right? Or is transparent.
Correct. It's very close. Well, the single level is transparent. As you go up, it gets more silver and blocks more light and more light. So they're looking at, I think it's multiple thousand layers for the full up space elevator. So this is
Oh,
not, it's not trivial. We would have to come up with rolls of it and then layer it. But I ask people, how many thousands of miles of toilet paper do we make? We make it and then we roll it up and then we sell it, And so the concepts are there about producing stuff and putting them in rolls. And we make aluminum foil and we make steel and we make a lot of things in rolled up mechanisms. So there's a lot of engineering know-how on how to produce long sheets and roll them up. And so, yes, it's going to be hard. Yes, it's an unknown process. Yes, we've got a long way to go, but we have the material now.
I'm just trying to understand what we have.
I don't understand it either, other than what I've just said. We have some experts in our International Space Elevator Consortium, and one of them is an Adrian Nixon up at the University of Manchester. He works with the university, lives right close. And he is a journal editor on graphene and publishes on graphene monthly, stuff like that. So he's the world's expert, and we use him a lot. He's on our board and he gives us updates. If anybody's interested in the material, if you go to our website, isic.org, and go to the newsletters, that we've got an archive of the last 8 years of newsletters. He's put in, now this is an estimate, 8.5 by 11 sheet of paper description of some aspects of the material every month for at least 5 years. So if you want to get an update on the material, you go to our archives, just start and go backwards on the material, and he updates it. He talked about being a shiny mirror. He talked about ripping. It's got a characteristic where it stops rips. And it's not like you go, if a rip occurs, then the material naturally binds again because they're atom to atom. And so
Right.
the atoms want to be bonded. And so
Right.
if
Yeah.
you rip it and you put them together, they'll tend to go back. Now, I don't know anything about that, man. I'm a mechanical engineer. I deal with wheels and stuff like that, big rockets and stuff like that. This material stuff is beyond my ken, but I can at least describe the top level stuff.
How easy is it to cut
I would
if you
imagine
want
pretty hard.
to? Okay.
Lasers work on anything, but I don't know the answer. I don't know the answer.
Okay.
There are a lot of answers I don't know.
Okay. So going back to space elevators,
Yes.
now that we've got material, where's the center of mass?
Okay. Let's talk about deploying it so you understand the physics of how it works. I actually taught orbit, so I know a little bit about this.
Oh, nice.
It turns out what you do is you have your full length tether. So it'll be 100,000 kilometers. This is our estimate. Who knows what the final one's going to be? You're trading mass above geosynchronous and mass below geosynchronous. You want the center of mass to be at geosynchronous plus or minus. It's usually a little bit above, but we'll get into that in a few minutes. Anyway, so you take your big mass, your roll of, and it certainly will not be a full space elevator tether. It'll be one that's robust enough to survive. And then we build up from the initial one, like a road. You put the first layer down, then you fill it up. Okay, so
Like Niagara Falls,
right.
the bridge across Niagara Falls. Apparently, they had a guy with a kite
Oh,
land the kite on the other side, so they had a string, and then they just bigger and bigger cables.
concept's the same. Okay, so what we're going to do is we're going to go up to geosynchronous with a rocket with enough tether to go up and down 100,000 kilometers on a big reel. And the simple concept is you just reel down. Okay, now this is a simple part. The kicker is that you want to have the center of mass base to geosynchronous. So as you roll down 100 miles this way, the big mass would go up 3 inches because it's more mass above than below because the tether's pretty light. You want to have an equal mass above and below. So you keep rolling out. So the upper one goes up. And then you get the bottom one down in the atmosphere, and you have some type of little airplane on it, a little buzz airplane or something, or wind oriented. You work it such that you can control it, the bottom, pretty easily. Then you grab it and you wrap it around something really, really, really heavy. And then you take and you aggressively move the upper one up. And the center of mass will be moved up above the geosynchronous actual altitude. And that will provide an outward throw, like a rock on the end of a string. You go like this, the rock is out there. It wants to go away, but the string is holding it back. So there's tension in the string as you do that. And as you get mass and velocity up, there's more and more tension. So we're going to be 100,000 kilometers up with a pretty good mass. And so there's going to be a lot of tension and everything else. And then you're going to have center mass still at basically at the center there. It won't move up because of the equalities. But anyway, so now you've got a solid space elevator. And now you take the little tether, adding additional stuff, running up the tether and gluing it onto the other ones, or running a single string down and weaving it down. We haven't really defined all that, but you would build up the tether just like you build up any other roads or bridges or anything else. And so we'd build up the tether so that it could have an initial capability. And then the initial capability, it would be a sheet of tether. Okay, we call it a tether, but it'd be a sheet. We've estimated 1 meter wide, but we haven't designed the tether climber, so it's irrelevant. But we're guessing 1 meter wide. And then you would put wheel on one side, the wheel on the other side, put pressure against them, and then turn wheel with electricity. So friction from wheel to tether will provide a force and you can climb. So literally you have wheels opposite each other, pressuring against the tether, turn wheels, go up.
Like a clamp.
Right. That's basically what it is, a big clamp. And
Mhm.
so we would have 4, 6, 800 wheels, whatever we work out. There have been multiple designs on the tether climber, and we're shooting for a 20-ton climber. Now, these numbers are all engineering estimates until we get the real math down. And so we'd have a 20-ton climber, and 14 tons would be payload. 6 tons would be needed for the wheels and the motor and the solar cells or whatever else and all that kind of stuff. So that's our estimate of how we would then go up. We'd have tethers like that. So everybody wants to talk about what happens if you cut the tether. Okay. The most probable severance of the tether would be down where the big space debris is. Now, I believe we can operate in the space environment safely. I've done 2 studies on them. They're on our website. Go look at them. 2 studies that say we can absorb the hits from the little stuff because this material is so strong. And we'll have a tether patching any little holes with this magic material that's infinitely strong. That's the way I look at it anyway. And so we're going to not worry about the little stuff. And that means up to maybe a fist size. We don't have to worry, it'll bounce off. 1 layer of this stuff is good enough for a protective vest for a policeman. Now, 1 layer is not going to do much good because the impact would really hurt. But if you put a layer outside of some real absorbent stuff and then put another layer below, all you need is 1 layer to stop the bullets. I mean, this stuff is so incredibly strong. We don't understand it. I mean, it's just so far beyond our comprehension right now. Anyway, so then the big stuff, we would have to move out of the way. And what we have is we have a mobile Earth floating on the ocean, and it would move one way or the other. So it would then put a sine wave in your tether, and you would plan for it not being where it would have hazard. So we definitely will need to develop a relationship with the people tracking the debris and predicting trajectories, the orbits of the debris for the next 24 hours, 48 hours. And then we would have that information coming into us and we would move the tethers. And I've actually spent a year tracking satellites and doing that stuff. So I think I understand that it would work. It will work if we work it that way. So we can work that. But if it were cut in the lower portion, we would just immediately release stuff from up at the geo and let the tether fall down and then grab it again. If it breaks between low Earth orbit and geo, which is very, very unlikely because there aren't that many satellites up there. There's GPS. We know where all those are and predict all that stuff. There would be meteorites, of course. You can't do much about meteorites. If they come and hit it, the probability is pretty low. It's like hitting a city or something that's pretty low. We haven't had that problem in a long time. So we would be tracking all those with the astronomers and all that, but we're probably not going to worry. If it were cut above geosynchronous, if it's cut below geosynchronous, the majority of the space elevator would go float out to Mars. But if it's cut above the geosynchronous area, which is even less hazard because there's not very many satellites out there, all that kind of stuff. And so we really only have to worry about meteorites. So we wouldn't have to worry really about that. But if it were cut above there, it would fall down. And it's so light, it would flutter down. We'd have to go then collect it. It'd probably go around the world. We'd go sweep it up or something. But it's really not that much of an issue. It would definitely be a lot of problems, but it's not catastrophic or anything else. But yes, the answer is we have to deal with all that. We have to work with all the space debris people. We have to work with the asteroid trackers, and we'd have to work with anybody who's launching a satellite going to the moon or Mars and make sure that we're not in any real issues. So there's a lot of cooperation we would have to develop between space operators and the space elevators.
How do you see getting the tether into place in the first place? Like rocket it up and then wind it down?
Yeah. You rocket it up to geosynchronous, and then you string it down and you string it up, and you'll have a tether then. Big reels of tether.
And then you said at the bottom you hook it onto something really heavy.
Right. Like an oil derrick or an aircraft carrier.
Okay.
It's not a trivial number. This is a big mass. Yeah, big mass.
Like an aircraft carrier's mass. Okay.
Well, I like aircraft carrier. Get one retired from the US. You have nuclear power. You have plenty of sleeping room. You have plenty of logistics area. You got a flat stack. It's perfect. I really like. I wonder if they got a spare aircraft carriers want to get rid of. We'll buy one or something.
So what's the timeline you're thinking for creating space elevators? Like 15 years, 20 years?
15 is a very good number.
Okay.
When you're doing a mega project, and this is defined as a mega project, usually it's over $1 billion in more than 10 years. But this is more like 15 billion in 15 years, something like that. And who knows how much it's going to cost? We don't know, but it's something like that. But if you take and put it in perspective of how much the richest people have, like Mr. Bezos and Mr. Musk, $15 billion is not that much. If you're going to put a bridge across the Thames to London, how much do you think that'd cost? A new bridge for London. I mean, it would be outrageous.
Billion.
Yeah, billions. And they just put a bridge between Malmo, Sweden, and Copenhagen, I think, or close to Copenhagen. How much did that
Okay.
cost? That was a lot. That was a lot of money too. So these bridges from one place to another are very, very important infrastructures, permanent infrastructures. And that's what we're providing. We're going to provide a permanent infrastructure. So the funding of a permanent infrastructure is different than, let's go launch a satellite. It's long duration, it's massive, and the rewards are huge, and the benefits for humanity are outrageously positive. We would enable the movement off planet. Everybody keeps talking about, oh yeah, we've got rockets to move people. That's very, very good. I love that. And I've been involved. I went to an Apollo launch and all that kind of, you got to be old to say that nowadays. But anyway, I went to an Apollo launch and all that kind of stuff. And I love rockets. But if you really think about what wins projects, it's logistics. We've got to support the people that are going. Mr. Musk has identified that he wants to put a lot of people on the surface of Mars in a settlement. To do that, he wants to put 1 million tons on the surface of Mars of supplies. If you do that math, that 1 million tons is 1% of the mass on the pad, what does that make the mass on the pad? It's a huge number. And remember that 80 to 90% of that mass, depending on which one, is rocket fuel, gets burned up in our atmosphere and leaves pollution. So we call our space elevators the green road to space because we don't ruin the atmosphere as we go along, and we don't leave any debris along the way either. So we're really the green road to space. So we have a lot to offer for the future movement off planet, one of which is we'd be the green road to space. We can lose massive, massive amounts of logistics to where they need to go. There's just so many things we can do that are just awesome.
So what's blocking you from building it?
Money.
Money?
We need to get a daddy rabbit or somebody to say, here's $50 million, go do good things to get it started. The sad story, and I can't go into this too much, is we actually had 50 million in the bank one time, and the person who was going to provide that passed away on us, and so didn't get there. But anyway, we had $50 million planned. We knew where to put it, what to do. We were going to put a lot of money into the graphene development and stuff like that, create a tentative CEO, create a financial office, have chief engineer. You know, we need to make an infrastructure that starts doing the real planning. We're saying, okay, here's a real plan. We need to start the testing of the material here. We need to start the testing of the tether climber here. Oh, we got to design the tether climber here. I've been on 3 mega projects before, and you really need a small, 5, 8 people is all. A small team getting together, putting their brains together and saying, these are the next step, next 6 months, next year, next 18 months. Here's what we need in funding flow. And let's start with you get 50 million, 10 of it will be on just getting people and buildings and stuff like that going together. But the 40 million you ought to put into projects. Let's do something on the graphene development. Let's do something on the tether climber power system. If you had $50 million tomorrow, I could get a team that could start space elevators.
Okay.
It would be an international team. It's probably not going to be in my local area, and I won't. By the way, I have no desire to be running that at all. I cannot commit that much time. I don't have that much energy. I've been on mega projects. It's 80-hour weeks for 2 or 3 years. You really have to buy into it and get into it and stuff. You get paid well, no doubt about that. But You got to be ready, committed to do that. So we need a team of 5 to 10 people that really, really believe in space elevators, want to come together. Nowadays, most of them could be Zoom or whatever, and then we can get together periodically for the big meetings and stuff. But we really need money and a small team to get kicked off. We could do that in a heartbeat. All we need to do is get somebody to say, "I have 50 million or 100 million," and just go do that. So we could go do that. And it's not that unbelievable that somebody would want to contribute to the future of humanity, and this would do it. This would be, we would have a green road to space. We could move massive amounts of logistics. We could make it happen.
Mm-hmm.
I keep chortling every time somebody says, well, we're going to get on the moon and we're going to mine the moon and we're going to take all these products and all this kind of stuff. And I keep thinking, yes, we can get on the moon. I can see that now. We can, NASA, Mr. Musk, Mr. Bezos, and a whole bunch of other people are enabling us to get on the moon. And I am 150% behind it. And they're doing a spectacular job. But when they turn around and say, where's my extra oxygen tank? Or where's my food for next week? Or, hey, we've got a guest coming over from the Chinese moon thing. We got to provide them some Chinese food. Where's our Chinese food?
Okay.
Okay, where's the logistics chain?
Right.
Have you ever heard about one?
Into space? No.
No, no. We could provide a logistics chain to where it needs to go. Initially at about 30,000 tons per year on the first setup of space elevators. And when we get going, 170,000 tons. So we could provide to Mr. Musk his million tons in like 8 years.
Right.
Okay, if you're providing 0.5% to the surface of Mars in rockets, how many launches is that going to take? How many years is that going to take? I did the math and it's really outstanding. It is so far over conceptually. You can't even conceive of the number of launches it takes to put 1,000,000 tons to the surface of Mars.
Right.
You do realize for his one vehicle, mission vehicle, to go to Mars, he has to have 10 launches.
Yeah, I can't remember hearing that.
It was 4 for the first 5 or 6 years. They recently, if you go look on the website, he's recently changed it to 10 launches to get one mission spacecraft going to Mars. Now, the mission spacecraft's a huge spaceship. It's huge. It can land on Mars and it can handle 200 people. It's a huge spaceship, but it takes 10 launches to get there.
Yeah.
Now, that's what I've seen. I certainly can't stand up and say I'm a part of their Mars program, but I've seen that on the website, 10 launches. You're sitting there saying, that's a lot of launches.
Um,
The bottom line is we provide logistics support. That's it.
going back to space elevators, and you're saying there'd be like a stop point at like geosynchronous orbit?
Okay, the new terminology. We did this stuff for 18 years and we really didn't come up with too many new terms or anything. Recently, I've come up with the realization that we have to match our terms with the space community so they can start understanding what the heck we're doing. So we come up with the terminology spaceport. Oh, wait a minute. Somebody else came up with that. Spaceport. So our one on the surface of the ocean, we call that the Earth spaceport. Right. Everybody buys into that. Yeah, we bring rockets there. We launch stuff. We land stuff and take it off. We load stuff. We do all that stuff, what a spaceport does. Mm-hmm. But the beauty of a tether, a permanent infrastructure, is that we could put a spaceport at geosynchronous. Release spacecraft, accept spacecraft, that match the velocity, come up, we grab it, we can refuel it, we could fix it, we could store it, we can, now this one's a biggie. This one took us a long time to figure out. It's silly. How long does it take to come up with ideas? Anyway, assembly at a spaceport. What you do is you take 14-ton payloads in each tethered climber. They come up one a day. Okay, one a day. 14 tons. Now you store it at the geosynchronous spaceport, and then you put 10 of them together. into a spacecraft. Oh, and aside, space solar power, I believe, will become a real program. And they're going to provide energy from geosynchronous to the surface of the Earth cheaper, better, easier, and much more efficiently than trying to do it on the ground.
Right.
So my belief is space solar power will occur, but nobody asks how big is a space solar power satellite. The smallest one, the smallest one is 2,100 tons, 2,000 tons, the smallest one.
Right.
So if we launch our logistics infrastructure and put, let's just say 21 tons on each to the climber, just exaggerate from 14. You let 21 tons a trip each day. What's that? It's 100 liftoffs to do one of their projected satellites.
Okay, right.
So what do you do with it? Well, you bring it up to our spaceport at geosynchronous and you get 100 of those, and then you assemble your spacecraft right there.
Yeah.
Okay. So it's assembly, which is a new offering from the space elevator community to the mission people, the customers. We can assemble your spacecraft at our spaceports. Okay, so we have an Earth spaceport. We have a geosynchronous spaceport designed for space solar power. We didn't do that specifically, but it's perfect for space solar power assembly. Then you go up to the apex anchor at 100,000 kilometers. Now, think about this one, the assembly of a science spacecraft. Well, right now, our first payloads would be 14 tons. Okay. If you look at all the science missions by NASA, none of them were 14 tons. The satellites were 1% of the mass on the pad that went to Mars, Jupiter, Saturn, and are beyond our solar system in the Voyagers. Those things are minuscule.
Yes.
Let's take that another step. It's an important step. If you have a minuscule satellite and you want to do 100 science missions on the end, everybody at JPL had their own science mission. Okay, I want to do 100 of them there. Okay, this is revolutionary science. I want to be the first scientist to collect X. Okay, you only have so many payloads you can put on. And there was something like 4 to 6. Wait a minute. Those guys could not operate all simultaneously 24 hours a day because there wasn't a big enough battery. Why wasn't there a big enough battery? Because you couldn't lift it off.
Right.
So our mission, our science mission satellites to our planets around the solar system and beyond have been spectacular achievements of engineering.
Yes.
But minuscule in scientific payloads. So what do we have to do? We have to become the supplier, the logistics chain. Now you bring up to the apex anchor and you launch a 14-ton satellite. Holy shit, those guys at JPL would have Christmas parties for us. But wait a minute, let's take it one step further. Let's say we put 10 14-ton satellites together and have 140-ton spacecraft. How much battery can you bring? How many science experiments can you come? Okay, then you put rockets on it to do trajectory stuff along that, but you assemble it up there at our spaceport. So the spaceport at the Earth, at Geo, and at Apex Anchor are the same thing. Release, accept, repair, refuel, assembly, and store.
Right.
So these spaceports are not only on the surface of the Earth like everybody else, but we're also at Geo and Apex Anchor. So we're trying to pass the word on to the space community that we have 3 major spaceports. And they all go say, yeah, we understand that one down there. What are these other 2? We've never called them spaceports before. So they never thought that we could assemble something there or repair or store. So we're trying to get the word across on spaceports as a very critical step in having the space community understand the strengths of space elevators. So your show here is going to be very important because it's the first time I've really talked about it
Okay.
in the space community. So this is a key discovery. It's more like a recognition instead of a discovery. Holy Toledo, what can we do? The answer is we're a spaceport.
So geosynchronous orbit, though, is like right where the Van Allen belts are, right?
No, 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 no. Oh, let's rephrase. There's radiation all out there.
Yeah.
The Van Allen belts are down, and they give us a problem in low Earth orbit.
Oh,
Our
okay.
medium Earth orbits have less radiation belts because the magnetic fields are what holds them in. Okay.
Yeah.
So there's less density in as you go up. At all altitudes, you have radiation. And all altitudes, you have issues that you have to deal with in that arena. But the dense stuff that we call Van Allen belts are really down toward the bottom. We have to deal with that in our spacecraft. So when we launch anything, we will be designing it for radiation protection. I mean, you just do that. And then when you get out beyond or geosynchronous, we then have all the cosmic rays that come in,
Yeah.
all the stuff that coming in out there. And we got silly things like neutrinos and all that stuff. So there's a lot of stuff up there. When you design a spacecraft, you go, okay, I finished designing it. And then you go, whoops, now I have to design it for the hazardous environment. Yeah, it's really silly. Example, to design something on the surface of the moon, you have to be able to have it go through 14 days of night, which is like 20 to 40 degrees Kelvin. If there's no sun, it gets really, really cold. And so plastics don't work in that stuff. And the environment you design for as a space engineer stretches the imagination sometimes. And you have to really, really work on what do I have to do here? Because this environment is different. But we pretty well understand radiation. We understand cold night, sunny day, because satellites are going in and out of the sun in low Earth orbit 14 times a day. So we understand the night sun duplex of a problem pretty well. As a spacecraft engineer, you have to design it the way you would for real normal stuff. And then you got to say, oops, it's not on Earth. We got to design it for all these other issues, radiation, cold, alternating cold, all that kind of stuff.
Well, all these other things. Would you be able to take passengers up your tether?
Yes. I
How long
started
would it
out,
take?
it's 7 days to Geo and another 10 to Apex Anchor. But
Oh,
let's take the Mars example. You can go up there, take a 7 and 10, 17 days to get there. Then it's only 61 days to Mars if you take the fast trip.
right.
Versus going on a rocket, which is 7 to 8 months. Okay, we will have people on space elevators. Let me put a comma there, or maybe it's a hyphen. I don't know. My suggestion that I'm going with is we design our first space elevators for logistics only, because the redundancy and the safety for the human inside the box is another order of magnitude beyond protecting a satellite. So we would have to have boxes that keep humans in there, temperature controlled, radiation controlled. We'd have to have bathrooms for them. They don't tend to work too well in space. We have problems here. We'd really have trouble. So my suggestion is we let the rocket guys do what they do best, which is move fast through radiation belts with people. And so we move people with rockets like they do now. It's a very good thing. So we want to team with rockets and let them do that. But when they get someplace, we want to have all the supplies there for them. And we want to keep them supplied. And we want to have emergency equipment. Let me give you an example. When we designed our Apex Anchor, we did a study for 2 years on Apex Anchor missions. We didn't worry about designing the thing other than sketching something. We wanted to go into missions. What can we do at the end of the tether? Well, one of the things we can do is astronaut rescue. We can put on the end of the tether extra oxygen, extra habitats, extra rovers, extra water, extra whatever, and have it stored at the end of the Apex Anchor. And then once a day, when it comes around where it can be released toward the toward the moon, we can release it and it's to the moon in 14 hours.
Oh.
I mean, it's really fast. You got to have a rocket retro and slow it down and land it. Okay, we got to have that on there. But still, we can get supplies to the moon in a day. Well, if you just miss it, it'd be 24 hours to get around. But you release it, and then it's 14 hours. And going to Mars, it's variable from 61 to 400. But each time you come around and you can release, you can go to Mars. So we can provide logistic support. Well, some of it could be emergency. Let me ask you this, and I've never heard of this. Is there any program around designed to rescue astronauts on the moon? Let's start with they have a 14-day window because it's going to be night pretty soon. And it really, really gets cold. And I'm guessing that NASA doesn't have any plans on people staying more than 14 days on the surface for a while. Yes, we'll go down for a few days and have a nice little moon village there for a while. But we're going to have to handle the night problem yet. We're not there yet, in my estimation. So we're going to have a capability to get the people off the surface if they run into problems.
Right.
Have you ever seen the words astronaut rescue in any of the Artemis work?
Can't say as I have.
Now, I'm not criticizing because we're doing something well beyond the normal. We're doing something remarkable. And I love it, and I'm 150% behind it. But when you sign up to go to the moon, you sign up for a very risky mission. By the way, I would go. I volunteered to go and be the guy in charge of toilets. Okay. I'll do anything, but especially I take care of the toilets. Nobody wants to do that. I'd love to go to space and go to the moon. It'd just be a highlight of my life, so to speak. But everybody who signs up signs on the dotted line, and it's risky. But we could provide extra oxygen, extra water, stuff like that at the Apex Anchor. Now, we're not going to be ready for 15 years, so it ain't going to help our Artemis crews and stuff like that. But we should look at the necessary missions for the Apex Anchor, and one of which is emergency supply or routine supply. Routine supply, run it up there 17 days and then release it when it gets around to the right thing and it gets to the moon in 14 hours. You have a retro rocket, you land any place you want. So we could be the routine supply chain for the lunar village, and we could just ship them stuff every day. 14 tons every day. If you think space elevator as logistic, permanent infrastructure, you have a different opinion of what you're talking about. It develops your mind so that it goes into a real positive state, which is we really need that. All it takes is $50 to $100 million to start it off. And I have no desire whatsoever to take any of that money. I'll help advise and everything. Maybe they give me a consultant fee or something, but I don't want to be involved in that. It's too overwhelming. It would crush whoever gets into it. We need a good 40-year-old entrepreneur and engineer who wants to do something for humanity and really wants to get into that. He or she could really, really have fun. I mean, it's going to be a hoot. A lot of problems, but it's going to really be a ride, man. It's going to be some heck of a mega project ride. It'd be fantastic. Plus, what they'd be doing to help humanity would be amazing.
So in one of the documents you sent me, your diagram showed like a one up tether and one down tether. Like your tether climber goes up one tether and comes down a different one.
Yes.
In the diagram, it showed like the ends of them quite far away. Like, how do you get from one to the other?
Careful.
Or is it just the way the diagram looked?
Okay, orbits wise, you're in trouble. Okay, no doubt about it. But if you come down to geosynchronous, okay, Apex Anchor, you're going so fast, you release, you're going to Mars. Okay, you might not have the right vector, but you're going enough energy to go to Mars. So releasing there is catastrophic if you want to come back down or something. So what you do is you go back down to geo.
Okay.
And now you just float over because you're at the geosynchronous orbit and you're the equal amount. You're at a location above the Earth that's rotating at the same rate the Earth is rotating. So you can just float from this point over there. I use the word float, but you're in orbit. You're just changing the velocity direction a little bit. And so then you either back up or go forward at the altitude of geosynchronous. And then you reach the other tether and you go down the other tether. So yes, it's a very simple thing to do at geosynchronous. At apex anchor, it's impossible.
Speaking of that, what's the G forces at the apex anchor? Is it like
2/10.
less than 2/10? Oh, okay.
Well, 2/10 of G. We wondered about that. Multiple people have calculated it's plus or minus. It's significantly less than 1 G. It's less than the gravity of the moon, even. It's very small. But it's in an outward direction, right? Because you're tossing it, so there's an outward force. So your infrastructure would be upside down compared to humans on Earth. The force would be outward. So to keep things on the table, like a drink or something, you'd have your infrastructure facing toward the Earth.
So you're standing there, you're either out, you look up and you're seeing Earth.
Right. Yeah. The Earth's above you. The answer is that you really can't do apex to apex anchor. The velocities are too great. But if you just climb back down to the geo, you just shuffle across. By the time we get this going, we probably have a tether between the two with tether climbers going back and forth. I mean, 100 miles or so. Let me take that back. I don't know how far it is. It's a significant difference. But you put it on a tether climber and go, it'd be easier just to release it and let it go. You just add a little velocity or subtract a little velocity, it goes the right direction, it gets where you need to go. We do that all the time in geosynchronous satellites. We change it from this location to that location, and we just do it all the time.
Right. Okay. So for our listeners, like students and young people, can you give any advice on how to get into this industry?
Okay. I've been asked that a lot. The first is, it's no longer just an astronaut industry. Okay, the old days was you had to be an astronaut, okay, or you had to be a big engineer or something like that. It's no longer that. We need everybody. We need lawyers, we need historians, we need electrical engineers, we need psychologists, we need everybody. Okay, so there is a job out there in the space industry for somebody who's really, really interested. So how do you get it? The way you get it is be the best you can. You do extremely well. You get recognized by your peers as a good person who is succeeding at what they're doing. That's what we need. We need good people who are motivated to work in the space industry and excel because they're good and they dedicate their activities, they work, they do. Let me give a little caution. My whole career has been 60-hour weeks. I mean, I can't remember too many 40-hour weeks. Even when I was shift work, I ended up doing stuff in addition to shift work because you're having fun. You're just doing things. I mean, I'm still working. I don't get paid, but I'm getting work 30, 40 hours a week, writing papers, doing stuff. I just enjoy it. And the kicker is you enjoy what you're doing. So then you do well. And then people recognize that you're good. And then you apply for the job and somebody says, oh, yeah, I know her or him. They do well. We need them. And that's my recommendation. There's no specific need for you at this particular point. Electrical engineer, mechanical engineer, space engineer, those are all big terms. We just need good people that have skill sets. The space arena is very rewarding, challenging, and consuming. And it's really the right place to be.
Okay.
It wouldn't be any place else. My wife and I have had a fantastic career. She's got a PhD in space policy and has been working with me. And she and I write most of these papers. You'll see her name on a lot of stuff. And we have a great time doing this. And it's just fun. Just a neat environment to be inside.
Speaking of that, who else should I talk to?
Well, the critical issue today is graphene. And so I would recommend Adrian Nixon. Then there's an entertaining guy who's really very, very knowledgeable, and he's an expert at physics and engineering and math and calculus and all that stuff. He really is good. And he's fun to talk to. And that would be Dr. John Knappman. And he's been one of our staunch supporters. He's been on our board for years and supports us. And he's in England. But anyway, those two are really worthwhile getting to and talking to. They would be good interviewees.
Okay. Any books you'd recommend?
Okay, if you're interested in space elevators, the best thing to do is go to our website, isic.org, and go to the studies page. We've got 16 studies. We just had a new one put in, which is powering the space elevator. How do we get power to the space elevator tether climber? A very
Right.
puzzling question. And that's just an example. We also have some that talk about space debris. We have one for missions at Apex Anchor. So we have the whole spectrum of space elevators laid out in academic research studies. And we've had inputs from college students and a whole bunch of other people from around the world in supporting these studies. So they're a quick read. You download them PDF. They're cheap, like free. And then you just scan the parts you're interested in. And there's some really interesting puzzles that are addressed that would bring you into the thing. The first thing you should do is go to our website, go to recent articles, and then go down toward the bottom and look at the two British Interplanetary Society magazines for the summer of 2023. One of them is called Spaceflight, and that's their top-notch big magazine that Arthur C. Clarke used to edit and all this kind of stuff way back when. And then their journal, which is more of a technical reports, long reports, a lot of good technical stuff. They did two dedicated magazines the same summer for space elevators. And if you read those, you'll be up to speed on what's going on in space elevators. Those 11 articles are very, very good, and they're inclusive of almost everything you need to know. And then if you look, then when you have questions, you go to the study reports or look at all the papers. We got most of the papers from the International Astronautical Congresses on space elevators for the last 20 some years. So if you go to the recent articles and go into the IAC, we've got all kinds of technical papers. So if you're really interested in space elevators, you could get consumed by going to our website and seeing the papers and everything else. But the way to start is go to those two British Interplanetary Society magazines. They'll cover everything you need to know about space elevators and more. You don't have to read all 11 articles, but they're really, really good.
Okay. You mentioned Arthur C. Clarke, and I remember the name of the book. It's Fountains of Paradise.
Fountains of Paradise. Yes, that's it. I've only read it twice. I'll have to do that. I haven't read it in a while.
I think I've only read it once, but
yeah,
that was like 30 years ago. But
yeah. Well, they're starting to get tethers and space elevators out there in the TV shows. And I keep but you know, they always want to talk about how dangerous they are. They cut them and they kill everybody. The answer is it's a logistics infrastructure like a bridge. If people want to blow up a bridge, they go blow up a bridge. But we're going to have a pretty good set of Marines there and a lot of radars keeping airplanes away. So we're going to be in the middle of the Pacific. Nobody's going to be there. Nobody goes there. You can't sail there because the winds are not very low because the hurricanes go north-south. The winds blow and go north-south. So along the equator, there's not much there. The protection problem for the tether at the Earth port, the spaceport, is not as draconian as it would be like for Cape Canaveral or someplace like that. If somebody wants to blow up a rocket, piece of cake. Anyway, so that's basically where I'm coming from on space elevators. If you want to follow up in anybody, they can go to our website and send us a note to info or whatever.
How was this talk?
I loved it. I enjoyed it. Of course, I do enjoy me talking. That's bad, isn't it, when I do that?
I like just like getting people talking and then just let them go.
Yeah, I know. Well, we make a mistake. We keep talking instead of listening. But anyway, it's a fun topic. I've always enjoyed it, and I do have a lot of knowledge that I like to share. So thank you for giving me the opportunity.
Yeah, thank you for coming on with me.